All right, let's start then. So today the topic is once again number theory, and I'm just going to continue to go through the worksheet that I was going over last lesson, and maybe like address some of your questions regarding number theory. So by the way, can I just have a show in the chat who was here last lesson? If you were here last lesson and remember the content, say type yes in the chat. All right. We have one yes from Jackie. Jackie, can you, if you still have the worksheet from last lesson, can you just work on the worksheet yourself for the first 10 minutes, and I will go over some basics to catch everyone else up to speed. Find the worksheet really quickly. There should be this worksheet called Mind and the Number Theory, Choose 6. Let me see if I can send it to you. I don't, no, I'll just send it in the chat. See whether it works. Oh, never mind. I'll just screenshot then. Okay. Can everyone see the worksheet? Great. So today, so basically all the problems except problem one is solvable by either one of the two theorems. The first theorem is named Chinese remainder theorem, and the second theorem is named Fermat's little theorem. Has anyone not heard of these two theorems before? Um, okay, let me ask the question another way. Has anyone heard of these two theorems? Has everyone heard of these two theorems before? Okay, I received one yes from Jackie and nothing from everyone else. So I will just go over them really quickly. And once again, Jackie, feel free to go like and do the later problems in the worksheet. Right. Let me try to start a whiteboard. Mm. One moment. Can you start a whiteboard so I can start drawing? Ah, there we go. So the first of the two theorem, Fermat's little theorem. Oh, the name. I'm sure the name sounds a bit familiar to some of you. Has anyone heard of Fermat's last theorem before? Fermat's last theorem is a really famous problem that was solved actually that was like unsolved for 300 years. Well, it's also a problem in number theory, and it took like basically all the mathematicians in the world like 300 years to solve it. Now, fortunately, Fermat's little theorem is, as its name suggests, not as hard as the last theorem before, because the last problem is usually the hardest, right? And it states a quite simple statement, which is, well, a to the power of p minus 1 is always divisible. Well, actually, not minus 1, minus p. Wait, no, minus a is always divisible by p, where p is a prime. Does everyone understand what divisible means? Oh, yeah, I assume everyone knows divisible is just saying, well, when you divide this by an integer answer, well, I mean, when you divide a to power p minus a by p, you get an integer answer. You don't get any fraction of this small. Now, for example, you can calculate that. Can someone other than Jackie? Thank you, Jackie, but you have been very but can someone other than Jackie tell me what is 2 to the power of 3 minus 2? Uh, just thank you, thank you, Jordan. Yeah, so it's 6, and as we can see here, 6 divided by 3 is equal to 2, right? So 6 is divisible by 3. That's like one example of Fermat's little theorem. So this is FLT, Fermat's little theorem. Now, let's use this theorem to solve a slightly harder problem. Okay, can you please, whoever that is, don't draw on the scribble on the whiteboard. Thank you. Yeah. So let's solve a slightly easier problem. Right. 3 to the power of say 11 minus 2. Is this divisible by 11? Does 11 divide 3 to the power of 11 minus 2? Yes, indeed. Right. If this is 3 to the power of 11 minus 3, it will be divisible. But because it's minus 2, it is not divisible. Very good, Josie. Thank you. All right, Josie, can you answer another question? What is the remainder of 3 to the power of 11 minus 2 mod 11 divided by 11? What is the remainder of this 1 3 to the power of 11 minus 2 is divided by 11? Yes, indeed. Because 3 to the power 3 to the power of 11 minus 3 is divisible, and so 3 to the power of 11 minus 3 plus 1, which is 3 to the power of 11 minus 2, has a remainder of 1. So yeah, very good. Thank you, Josie. All right, let's move on to an even harder problem. Let's move on to an actual question on the worksheet, which asks, is 3 to the power of 16 minus 2 to the power of 16 divisible by 17? Anyone? Alicia, what do you think? Adrian, what do you think? Adrian. Okay. What about you, Jackie? What do you think? Why not? Oh, sorry. Maybe I forgot to mention before, but the theorem only works when P is prime, and 16 is not a prime, so you cannot apply the theorem this way. Um, so personally, how I do it is 3 to the power of, so 3 to the power of 17 we know has a remainder of 3 mod 17, right? Because 3 to the power of 17 minus 3 is divisible by 17. So 3 to the power of 17 has remainder of 3 mod 17. Now we can actually divide both sides by 3, which gives us 3 to the power of 16 is equal to 1 mod 17. This is actually another formulation for the theorem. So you can phrase the theorem as stating that a to the power of p minus 1 has a remainder of 1 mod p. Um, for for p doesn't divide a. Right, so 3 to the power of 16 has a remainder of 1 when divided by 17. Now, can someone tell me what's the remainder of 2 to the power of 16 when divided by 17? What's the remainder of 2 to the power of 16 divided by 17? Yes, very good. Thank you, Josie and Jackie. It is 1. So 2 to the power of 16 is also 1 mod 17. All right, so can someone tell me what is the remainder of 3 to the power of 16 minus 2 to the power of 16? Yes, so is it divisible or not? Yes, thank you. So yeah, the answer to this question is yes, and the proof is, so I'll write all the proof. Um, because remember, in Math Olympia, we always need to justify what we're saying. So answer, yes. Proof, by FLT. 3 to the power of 16 minus 2 to the power of 16 is equivalent to 1 minus 1, which is equivalent to 0 mod 17. And then we're done. All right, so see, that's a quick question, a very elegant question. Solved in one line by the all-powerful Fermat's little theorem. Now let's go a bit more advanced. All right, what is 3 to the power of? So what is the remainder of 3 to the power of 17 minus 2 to the power of 17 mod 17? Yes, 1. It is just equal to 3 over 2, which is equal to 1. Very good. What about 3 to the power of 18 minus 2 to the power of 18? Yes. Jackie, can you please explain how you got the answer 5? Yeah, very good. So this is equivalent to 3 to the power of 2 minus 2 to the power of 2 mod 17, which is equal to 5. Now, what about 3 to the power of 19 minus 2 to the power of 19? Hi, Mackie. We're just going over the same worksheet from Mackie, Marcus, were you here last time? Cool. Yeah, we're just going over the same worksheet from last time. Some of the other people in this meeting wasn't here last time, so I'm just going over the basics, Fermat's Little theorem and Chinese remainder theorem again. Now, if you already know these two theorems, feel free to work on problems 7 to 10 in the worksheet from last time. Otherwise, you can listen along if you need a refresher. Anyways, what is 3 to the power of 19 minus 2 to the power of 19? Mod 17. What's the remainder when they're divided by 17? Joanna, what do you think? All right. Adrian, what do you think is the remainder of 3 to the power of 19 minus 2 to the power of 19? Well, let's do the calculation once again. So notice that 3 to the power of 19 is equal to 3 to the power of 16 times 3 to the power of 3 minus 2 to the power of 16. Yes, 19 is correct, but because we're doing mod 17, we take the remainder of that, so it'll be 2. But thank you, Josie. So yeah, you can revise it as this. And remember that 3 to the power of 16 is just equivalent to 1 under mod 17. So this is 1 times 3 to the power of 3 minus 1 times 2 to the power of 3, which is equal to 19, because 3 to the power of 3 is 27, 2 to the power of 3 is 8, right? 27 minus 8 is 19, which is equal to 2 mod 17. Great. What about, can someone tell me about 3 to the power of 32 minus 2 to the power of 32? Yes, thank you. Thank you, Josie. Oh, sorry, Jackie. I meant 3 to the power of 32 minus 2 to the power of 32 mod 17. And yeah, I was looking for the answer 0 mod 17. Josie, can you please explain why we got 0? Give something of a proof along this line. It's actually 1 minus, yes, 1 minus 1, yeah. So we can rewrite this as 3 to the power of 16 times 3 to the power of 16 minus 2 to the power of 16 times 2 to the power of 16, which as we know is equal to 1 times 1 minus 1 times 1, which is equal to 0. Um, so yeah, just that, so yeah, as you can see here, this hints at some, very circular, well, a pattern, you know what I mean? Um, so what this means is that, when we look at a really large power, there's actually a way to break it down. Maybe 17 is too big of a number here. Maybe let's look at, 3 to the power of, say, 5, 3 to the power of, I don't know, something mod 5, right? So 3 to the power of 1 is, so let's say mod 5, in mod 5, the remainder of 5, so 3 to the power of 1 is 3, 3 to the power of 2 is 9, which is 4 mod 5. It's 3 to the power of 3 is 27, which is 2. 3 to the power of 4 is 81, which is 1. And then 5 is 3, 6 is 4, 7 is 2, 8 is 1, 3, 4, 2, 1, 3, 4, 2, 1. You guys notice how, when we start raising a number to power of something, its remainder, when divided by a prime number, starts repeating after a while, right? More precisely, the remainder of an integer power repeats with pattern p minus 1, with period p minus 1. So if we're looking at the powers of 3 mod 5, we see them repeating for every 4 numbers. If we're looking at the mod 2, we see them repeating. Actually, mod 2 is not a good example. Let's say mod 3. Oh, wait, no, mod 3 is also bad. Mod 7, why not? If we look at the mod 7, it's 3, 2, 6, 18, that's 4, 12, 5, 1, 3, 2, 6, 4, 5, 1. Right? No. The remainder of the powers of 3 when divided by 7 repeats with period 6. Right? When they're divided by mod 17, they repeat with period 16. And so this gives us really useful tool when we're dealing with, really large powers. Like say, for example, what about 3 to the power of let's say 1 million. Right? What is 3 to the power of 1 million? If you want, you can actually try input this into a calculator. What does a calculator say about 3 to the power of 1 million? What does a calculator say about 3 to the power of 1 million? Well, if you use a scientific calculator like mine, it'll probably say math error. By the way, David, can you please mute yourself unless you're asking a question? Thanks. Right, this number is too large. Your calculation and your computer, I don't think even a supercomputer can compute it. Right, not even if they have started computing it, like starting from the start of the universe. Right, this is so astronomically large number. However, Fermat's little theorem can tell us its remainder about 5. Right. Can someone tell me what is the remainder of this supermassive number when divided by 5? Yes, very good. Thank you, Jackie. Why? Because Fermat's little theorem implies that the remainder of 3's integer powers when divided by 5 repeats with period 4. 3, 4, 2, 1. 3, 4, 2, 1. So even if we have no way of calculating what this exact number is, we can still calculate, we can still find out something about its remainder. And personally, I just find that really cool. You know, it's like, what is one example? It's like, that gun in Minions that they use to, turn the moon into the size of a tennis ball, right? It just like, it just instantly obliterates massive numbers. So yeah, pretty nifty. Let's see if we have more problem in that worksheet. All right, let's look at those problems right now. Now, this problem is requires some more advanced thinking, but do not worry, it is completely solvable in like half a page by Fermat's little theorem. However, and to start off, I recommend you all to try some small cases. Right? What is n is equal to 1? What is n is equal to 2? What if n is equal to 3? Try these small cases and then tell me what you think the answer is. In fact, if I were you, I would probably try the first 10 numbers of first 15 numbers of it. Actually, 15 is probably too much. 10 is probably good enough, but I'll definitely try 10. Oh, by the way, does everyone understand what relatively prime means? So relatively prime means, so two numbers, A and B, are said to be relatively prime if and only if the greatest common factor, is the greatest common divisor, is equal to 1. So for example, um, 9 and 10 are co-prime because 9 is 3 times 3 and 10 is 2 times 5. Right, so they're relatively prime. They don't share any factors. Uh, However, 2 and 10 are not because they share the factor 2. So yeah, that's what relatively prime is. Right, it has been a few minutes. Everyone has had a go at least calculating the values of A1, A2, and A3. Can someone tell me, type in the text in the chat, what is A1? Yeah, very good. A1 is 10. And what is the prime factorization? Yeah, 2 times 5. What is A2? Very good. 48. Prime factorization. Yep. Can someone other than Jackie tell me what A3 is? Mackie. Oh, thank you, David. Uh, yeah, 250. Prime factorization. Um, yes. Thank you. Um, A4. Oh, by the way, usually in Math Olympiad, you're not allowed to use the calculator, but I'll be merciful here, and you're allowed to use calculator for just once. Only this time. Yeah. Um. Anyways, let's A4. Alicia, what is the value of A4? Does anyone know? Josie, what is the value of A4? Cool. Thank you, Jackie. Yeah, 11392. And once again, prime factorization, please. Oh, we're just using this formula over here. So an is equal to 2 to the power of n plus 3 to the power of n plus 6 to the power of n minus 1. So we're plugging in values of 1, 2, 3, 4, and 5 for n. Does that answer your question, Jonah? Uh, yes, David, indeed. It is 212. Yeah, thank you, David and Jackie. It's 2 to the power 4 times 3 times, oh, interesting, 29. Right, that's a quite big jump from 5. All right. Now moving on to A5. Once again, you're logging the calculator. Oh, we have limited time, so I'll just say it. Yeah, it's 8050, and its factorization is 2 times 5 to the power 2 times 7 times 23. Now, A6 is 47448, and its factorization is 2 to the power 3 times 3 to the power 2 times 659. Yeah, we're dealing with really big numbers here. 7. 282250. 2 times 1253 times 1129. 88. 1686432. 2 power 5 times 3 times 11 times 1597. All right, we'll stop here for a second. So, what numbers do we know are not what positive integers can we not exclude from the answers to problem 7? Because the question asks for all positive integers which are relatively prime to all the terms of the infinite sequence. Now, if a number is not relatively prime to even one of these terms, then it's out, right? So, yeah, thank you, David. We can immediately exclude all the even numbers. And let me just write some numbers out. 9, 10. Yeah, we can cross out all the even numbers. And yeah, very good. All multiples of 3, because, you know, um, we have like A2 is divisible by 3. And so none of these multiples of 3 would be co-prime, relatively prime with A2. So we can cross out all multiples of 3. Yes, Jackie, very good question. 1 would be considered relative. 1 is an answer because 1 is relatively prime with everything. So yeah, 1 is an answer, but we already excluded, but now we have excluded all multiples of 2, all multiples of 3. What else can we exclude? 5? Yeah. 5 because A3 is divisible by 5. Then 7 because A5 is divisible by 7. And also all multiples of 5 and all multiples of 7. So, so yeah, can someone guess what the answer to problem 7 might be? I don't need the full proof right now. Yes, thank you, Josie. Right, it seems like this pattern will continue forever and will end up crossing out every number except one, right? It seems like one will be our only survivor. So yes, that's the answer. However, we're still quite far away from proving it. You know, we can make the argument that, well, it seems like the pattern will continue forever. However, this would not constitute a proof, right? In order to prove that the answer is actually one and only one, we need to use Fermat's model theorem quite cleverly. So let me write out a few more numbers. Let me write it out all the way to 11. Hold on, I'm pressing a calculator right now. Right, I'm not even going to write out the number, I'm just going to write out its factorization. Because, number itself is meaningless to us, it's only its factorization that really matters. Right. We'll stop here because the numbers are getting too big even for my calculator. So we tried 11 small cases. Well, I wouldn't exactly call them small, but they're definitely smaller than the rest. And now we're trying to, see some patterns here that will help us apply Fermat's theorem cleverly. So, okay, I'll give everyone until 7:20 to try to find some pattern in this in these series of numbers. All right. So yeah, we have one very nice observation from Jackie, which is that, you know, when n is prime, when n is prime, a n is equal to 2 plus 3 plus 6 minus 1, which is equal to 10 mod n, when n is prime. Very nice. However, it doesn't really, well, actually, well, this will be useful later. But before it can become useful, we need to make a few more clever observations. So now I ask you to observe. Uh, no, I'd like to observe. I'd like you to observe. You know, where does each number stop working? So what I mean by that is, well, from the start, if it's clear that 2 and all even numbers don't work because the first number is already divisible by 2. Well, actually, all of those numbers are divisible by 2, right? And then 3. 3 stops working at A2. Okay, so 2 applies to all of them, and then 3 is here, and then here. Now, where does 5 appear? 5 appears here, 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 here. Right. Where does 7 appear? Well, 7 appears here. And here. And then what about say what's the next prime number? 11. 11 appears here. And does 11 appear anywhere else? Right. And 11 doesn't appear anywhere else. And 13 stops working here. Cool. All right, we have an interesting conjecture in the chat that they stop working at the prime before. So 5 stops working at 3. 7 stops working at 5. 13 stops working at 11. So for that, the pattern seems to hold. But 11 doesn't really follow the pattern because 11 stops working at 9, which is is not a prime. Oh yes, 11 is also in A8. That's right. Thank you. However, we can find an even simpler relation, but we can put a little twist on what Josie said. So as we can notice, 5 stops working at 3, 7 stops working at 5, 11 stops working at 9, 13 stops working at 11. Right. Thus, it's just P prime minus 2. Right? Everyone see the pattern? Sure, 11 also apply, here in 8. Yes, sure. However, let's just ignore those noises for a moment and just notice how they stop working. 2 and 3 are exceptions, but for every prime number that's bigger than 3, they stop working at p minus 2. Can everyone see that? 13 stops working at 11, 11 stops working at 9, 7 stops working at 5, 5 stops working at 3. So let's go back to Jackie's discovery about how. Uh, all right, good question, Matthew. Why are we ignoring 1188? Well, it just doesn't matter, right? The appearance of 1188 uh, doesn't deny the fact that P always. So right now we're just trying to prove the statement A always divides uh, A P minus two, right? This is always true. Even though 11 appears in A8, it doesn't contradict the statement. We're not ignoring it, it just doesn't really matter. Kind of sad. Um, yeah. So let's go back to the discovery by Getty that an always has remainder 10, not n, for n is prime. Now, I ask everyone to put a little twist on it. What is an minus 2 mod n? When n is prime. Now, instead of looking at an, I want you to look at an minus 2. I will give you guys until 7:30 to come up with an answer. All right, it's 7:30. Does anyone have any has anyone made any progress that they'd like to share? No. Okay. Well, me neither. However, so because n minus two is so Fermat's Lewis theorem tells us about what n is, and what an minus one is, right? But it doesn't really say anything about an minus two. So I'm kind of stuck as well. But that's okay. However, that's okay. I will look at an and then an minus 1 and see if that can give us any inspiration, right? So an is equal to 2 to the power of n plus 3n plus 6n minus 1, which is equal to 2 to the power of 1 plus 3 to the power of 1 plus 6 to the power of 1 minus 1, equivalent to, sorry, not equal, which is equivalent to 10, as Jackie correctly stated. Remember here, n has to be 10. N has to be 5. Right? And what is an minus 1? Well, an minus 1 can someone tell me in the chat what is an minus 1? Yeah, very good. It's 2 to the power of 0 plus 3 to the power of 0 plus 6 to the power of 0 minus 1, which is equal to 2 mod n. By the way, remember that any number raised to the power of 0 is equal to 1. So this is just 1 plus 1 plus 1 minus 1 equal to 2. Great. So now we have, this pattern. 2 examples. What is a minus 6? Well, I'm just going to be a bit cheeky here, and I'm just going to say yes, thank you, David. um, yes, I'm going to do exactly that, and that is going to be equal to 0 mod n. Yeah, that's it, guys. Can I have a round of applause in the chat? Thank you, thank you. Unfortunately, that is just wrong. Can someone tell me why I just did something that's really bad here? Yes, they spike right now. Yeah, can someone tell me in the chat why? Why did something really bad here? Well, the mistake I made here is I committed to the dark magic of being, yeah, exactly. It's integers, right? Like, what does it even mean for a number to have a remainder of 0.5 mod n? You know what I mean? Like, what does a remainder of 0.5 even mean, right? You can't have, we're doing integer division here. You can't have a remainder of 0.5, right? You can't have a remainder of 0.333 recurring, right? That's just plainly, wrong, right? That's illegal move here, right? So you can't do this. So we're stuck once again. Yeah, what do we do? What do we do here? How do we reconcile ourselves with the great sin we have just committed against the gods of number theory? Like Fermat will literally be crying and be rolling in his grave right now if he saw this. But there's a saving grace. There's something that we can do that thinks even more like black magic that can save us from this mistake. Thank you very much, David. Yeah, very good. Yes, very good, very good, very good. Can we multiply them to make integers? What do you want to multiply them by? Yes, very good. Six. So 6 minus 2 is equal to 6 because 6 is like the common denominator, right? Um, Now, can someone tell me what this expression evaluates to according to Fermat? 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 I don't even know. My pronunciations are bad. Uh, but yeah, what does this? Guys, what does this evaluate to? Remember that we're allowed to multiply remainders as if they're not normal numbers. Oh, also, I forgot to multiply 1 by 6 as well. Mackie, do you know what does this expression value to? Yes, indeed, it is 0. Um, can you explain why it is 0? Yeah. What is your working? Yeah, it's something like that. So I'll give a proper working. So you can rewrite this as 3 times 2 to the power n minus 1. So I moved a factor of 2 from 6 to 2 here. So it becomes 3 times 2 to the power n minus 1. Similarly, you can move a factor of 3 over here, which gives you 2 times 3 to the power n minus 1 plus 6 to the power n minus 1 minus 6. Now, guys, what is this according to Fermat? Right? That is 3 times 1, right? Now Fermat will here applies, right? So this becomes 1, and this becomes a 1, and this becomes a 1. So so this whole expression is going to turn into 3 plus 2 plus 1 minus 6, which is equal to 0, not it. And now everything we did was perfectly legal. There's nothing involving, there's nothing involving fractions or decimals, right? Everything we did was in terms of integers. Cool. Any questions? All right. So we're quite close to a full solution now. We just need to do a few finishing touch. So n divides 6 times an minus 2 for all n is prime, for all prime n, right? And so that means and but if if n is not 2 or 3, right? If n is not 2 or 3, that means because in that case then 6 doesn't really matter because 6 is co-prime. 6 doesn't, it means that n has to divide an minus 2 itself, right? Because the 6 doesn't contribute any useful prime factors when n is not 2 or 3. So when n is something like 5, right? If 5 can divide 6 times something, if 5 can divide 6 times a, then 5 must also divide a. Right? If 7 can divide 6 times a, then 7 must also divide a itself. So we know that when n is not 2 or 3, n always divides a minus 2. And indeed, that is what we're trying to prove over here. Right? 5 divides a3, 7 divides a5, 11 divides a9, 13 divides a11. So this means that we know all multiples of 5, 7, 11, all multiples of any prime bigger than 2, bigger than 3 cannot work. Right? So all multiples of a prime bigger than 3 now for 2 and 3 it's quite trivial because well for 8 but also notice that 2 and 3 divides a2. So all multiples of 2 and 3 can't work either. So the only number that works is 1, and we're done. All right. Any questions? Oh, yeah, that's fine. And so that is true by Fermat's theorem, right? Remember Fermat's theorem basically implies that there is there's a pattern, repeating pattern for the remainder of integer powers, right? Namely, when AP minus, so the remainder of AP minus 1, AP minus 1 is always equal to 1 mod P, right? And if you multiply both sides by A, you get A of P is always A mod P. And that's the same as A1 mod P. Does that answer your question, David? All right, great. Any other questions? All right, congrats everyone. I think that should be the first time for most of you. We just solved an IMO question. It was IMO 2005 question 1. So yeah, good job. It's not that bad, right? I hope everyone enjoyed it. Anyways, was it 2005 question? Let me just check real quickly. 2005. I'm wait, no, it might be question four. Oops. Anyways, it appeared on like IMO once. I'm pretty sure about that. So yeah, fun problem. All right, moving on. I think that's all I wanted to yap about Fermat's theorem today. I guess I can yap a bit more about Chinese. Oh, we have 15 minutes left. Should I yap a bit more about Fermat? Oh, why not? We have 30 minutes left. Might as well just like solve the last question, right? Can't be that bad. Yeah, guys, just try the last question. Oh, it's IMO question four. Yes, try Q10. Oh, by the way, is everyone on the Bible? Because it says that only four people are following me, and we have six people in this meeting. So we're missing two people. Oh, okay, I see. Yeah, that's fine. As long as you can see the whiteboard. Yes. One more minute on questions then. All right, time's up. Yeah, do we have any ideas? Can we have a discussion in the chat, please? Um, Adrian, what are your deductions so far? What have you tried? No answer. Okay. Josie, what have you tried so far? What about you, Jackie? What have you tried so far? Personally, I just wrote down the basics. We know, given by the question, P, oh, let's mean, P divides AP minus 1. What else does P divide? Well, thanks for that. P divides AP minus A, right? Just writing down the basics. No. Can someone tell me one more thing that P divides? Mm, I wouldn't say that. I don't think P actually divides AP. Um, but what I know is P divides the difference, which is A minus 1, right? If P divides two numbers, P must also divide the difference. Can everyone see that? Right? If P divides M and P divides K, P must also divide M minus K. For example, mm, right? So we know for sure. Sorry, does anyone want to say anything? Like ask any questions? Like, does anyone want me to explain why this is true? Well, this is true because, well, if P divides M, then we can write M as M is equal to, let's say, P times X, right? If P divides M, that means M can be written as P times X. And similarly, if P divides K, then K can be written as P times Y. Right, so M minus K is equal to Px minus Py, which is equal to Px minus Y, which is evidently divisible by P. And so we know that P divides the difference between these two, which is A minus Y. So let's say A minus 1 is equal to, no. Can someone give me a variable name? Like, what's your favorite letter? That's not A or P. Type your favorite letter in the chat, guys. All right, B, why not? Let's use B. Let's say A minus 1 is equal to B times P, because we know that P divides A minus 1. Now, what is A? A is BP plus 1, right? Now, what is bp plus 1 to the whole p minus bp plus 1. Has anyone done binomial expansion before? Binomial expansion, anyone? Well, actually, never mind. We're looking. The question is asking for AP minus 1, so it's BP plus 1 12 P minus 1. I'm just rewriting somewhere else. So AP minus 1 is equal to BP plus 1 P. And if you have done binomial expansion before, which I assume, okay, maybe you have not. So I will just quickly go over binomial expansion in 1 minute. Now, usually that takes like one lesson in year 11 or 12, I forgot. But we're pretty advanced here, so I'm just going to go over it in 1 minute. So, x plus 1 to the power of 1 is equal to x plus 1. X plus 2, x plus 1 plus 2 is equal to x squared plus 2x plus 1. X plus 1 cubed is equal to x plus x cubed plus 3x plus 3x plus 1. Now, and the pattern goes on and on. And this is what we call binomial expansion. Bi means you have two terms. The expansion means expanding the bracket. Now, if you write the coefficients out, you'll notice that the coefficient follows 1, 1, 1, 2, 1. Notice how it's, x squared plus 2x plus 1. Then 1, 3, 3, 1. Then 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. And this triangle is what we call Pascal's triangle. Now, it's a lot of interesting properties, but we actually just ignore all of that because it's not an answer to this question. But basically, how it tells us is x plus 1 to the power of p, to the power of, let's say, n is equal to a bunch of terms, and then which we're not going to be bothered to figure out because it's too large. But notably, the last two terms will be nx plus 1. Because the last number is always 1, and the second last number is always n. So the expansion of x plus 1 plus n is going to be equal to dot 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 plus nx plus 1. So what does this say? Now plugging in x is equal to bp, what does this say about the last two terms? Yes, what does this say about the last two terms of this expansion? Alicia, what will be the last two terms of the expansion of bp plus 1 to the power of p? That's okay. Let's look at this. The last two terms is nx plus 1, and where n is replaced with p, and x is replaced with bp. So the last two terms will be equal to p. Yes, very good. Thank you, Josie. Bp squared plus 1. Oh, and then because we have a minus 1 here, so we move the minus 1 over here. Minus 1. Now, plus 1 and minus 1 cancels out, so It's a bunch of things plus BP squared. Yes, just BP squared. So yeah, and what is the question on us to prove? I want to prove that P squared divides dot 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 plus BP squared. Well, P squared most definitely divides BP squared, right? That's just obvious. No, what about the dot dot dot? Well, the reason why we only look at the last two terms is, well, what do I mean by the last two terms? I mean the smallest degree. So everything that went before either something something x squared, something something x cubed, something something x, 4x a x b, all the way to x n, right? So in our case, that means everything dot 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 is in the form of bp to power of p plus bp to power of something something coefficient, some coefficient p minus 1 dot 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 all the way until bp minus squared, right? The degree, the range to at least a square, right? They're at least a square. Right? Some of them are cubes, some of them are like raised to power p. But it's quite clear that p squared is going to divide all of them, right? But the smallest of them is already a square, already contains a p squared. Right? Some of them contains like p cubed. Some of them contains like p to the power t. Right? So p squared would obviously divide everything in dot dot dot. And so we're done. All right. Any questions? That's the end of the lesson, by the way. So feel free to leave if you don't have any more questions. You're welcome. You're welcome, David. Great observation on the multiplying both sides thing. Hey, Adrian, do you have any questions? Are you still there, Adrian? It's the end of the lesson.